Talking with Dr. Osborne yesterday about the recorded lectures and whatnot, and I thought I'd be willing to bet that the students don't even remember that I have tutorial things there on the YouTube playlist. So just to remind you, here's the YouTube playlist for tutorials, not for lectures, and you have things that will help you for the test: the construction using ray diagrams and the different variations, because you're going to have one of these bottom four on the test. And so, a tutorial on how to do it. I think in one of them my phone rang. Sorry about that. But just a reminder that we have those there to help you out. Everybody knows how to get there, right? There's a link in Moodle. Okay, we're going to continue on talking first about optical instruments, talking about telescopes specifically. We're not going to talk about cameras. I decided I'm just going to cut that out for time. And then we'll start talking about interference. So first, a clicker question dealing with what we talked about last class period. As discussed, the object is placed at the focal point of a simple magnifier. Where's the image produced by the simple magnifier? Now, this was for the easiest viewing. Okay, everyone's answered. I have to look at my roster to make sure who's here and who's not. So we had 5, 2, 10, and 1. Okay, so 10 people said infinitely far away on the same side as the object. That is the answer I was looking for. We had it. This was the same question we had at the end of last class period. And I pointed out that it could be on the opposite side. It would mean the same thing, except for since we can only focus on the side that's in front of us, that's where it would be. Now look at the homework problems. You have problems where it's not placing the object at the focal length of the simple magnifier. Remember, the eyepiece of a microscope or the telescope we're going to cover next is a simple magnifier. That's all it's doing, is a simple magnifier job. But if the object, what is the object for the eyepiece of a microscope? It's the image produced by the objective, right? When you're doing multiple lenses, the first lens makes an image, and that image becomes the object for the second lens. And so if that object is farther away than the focal point, then what's going to happen? Let me draw a picture. So now I'm just looking at the eyepiece, the simple magnifier. If I have the object out here, where's it going to make an image? What kind of image? It's going to make a real inverted image on the other side. That's not going to be a very useful eyepiece. If you put your eye up here, and the image is formed out here, well, you can't focus on that. You can't see that. So that would not work for you. The object is going to have to be at the focal point or closer. So if you put it closer than the focal point, then you're going to have the image, instead of being infinitely far away, it'll move in. In my previous statement, in the question here, I said that the object is at the focal point. Why do we prefer having the object at the focal point rather than closer? Because your eye can relax for viewing. So it's about the relaxation of the eye. What would give you the biggest magnification? if it's closer, if you bring it closer so that the image is formed at your near point, that's going to be the biggest magnification possible. But then you have the eye strain. Now in your homework problems, you have a problem where, it's somewhere in between that. And so if it's somewhere in between, you need to find the angle for the aided vision. And the angle for the aided vision, you're going to have the object here and the image here. They're both on the same line. What ray do we call that line? The vertex ray. So if we have the distance object and the height of the object, that gives us the angle using the small angle approximation opposite over adjacent. And so you have to use that in solving for, what's the eyepiece magnification going to be when it's not at the focal point. So I want to make sure I cover that. Also, I have to point out something Aaron asked me about the last question. And when I looked at it, I realized it can't be the question that I thought it was asking. Because it says you have a 10 centimeter focal length, and how long does the microscope have to be to make the magnification 4 times what it gave you for the magnification of the objective. And with the numbers they gave you, you had the focal length is 10.0 centimeters. Its focal length is 10 centimeters, and you have a normal eyeball, that is n is 25 centimeters. What's the maximum magnification that you can get for angular magnification for that eyepiece? Do you remember? It's going, the n over f is the magnification if it's unaccommodated. That is, if it's easy to view. When you bring it in, so the image is at your near point, that's going to be the maximum magnification, and it only added 1. We did this calculation. And so that would be 25 over 10, 2.5, plus 1, 3.5. 3.5 is not going to ever equal 4. So they can't be saying, where would you have to put this to have the angular magnification of the eyepiece being 4, because that's not possible. Which means that you have to drop to the other kind of magnification, the first kind we found, the one that deals with the height of the image and the height of the object. And so for that problem, it's confusing in that usually we mean the angular magnification in the way it's used. But you have to use for that problem. So problem, and for both A and B you're doing this, but for A it was the objective, you always calculate what we call the transverse magnification. So for problem 5, for both, the magnification is equal to the height of the image over the height of the object, which is minus the distance image over distance object. And notice you have a simple relationship that says that the distance image is equal to minus m distance object. And so you have a simple relationship between the image distance and the object distance that you combine with the thin lens equation to solve your problems. So you're simply, for part A, you're finding distance image. Exactly that, imagine it. Or no, maybe you're finding the distance object for part A. For part B, you need to find the distance image for the objective, and then you need to find the distance object for the eyepiece, and you add them together to get the total length of the microscope. Since, the microscope has 2 lenses, the separation between them is distance image for the objective plus distance object for the eyepiece. Okay, that covered. Let's go to telescopes. We talked about microscopes. I gave you a clicker question about what the purpose of a microscope was. Now that you've answered that, just blurt it out. What's the purpose of a microscope? To magnify something that is small and that is assumedly nearby because it's small. If it was far away and small, we just wouldn't see it. The purpose of a telescope is different. Tele means far, so the purpose of a telescope is to magnify something that's very distant. because it's very distant, it again makes a small angle with the eye. So for instance, if we're looking at a crater on the moon, the crater on the moon makes a little tiny angle with the eye. And so we use a telescope to make it, after we view it in the telescope, make a bigger angle with the eye. That's the point of the telescope. So we're again looking for an angular magnification. And just like with a microscope, we're going to have an objective lens that's going to make a real image. And then we're going to have an eyepiece to give us a virtual image that we view. Now there are two designs shown here. This one here is our traditional microscope. And the one on top is the one that Galileo developed, called the Galilean telescope, traditional telescope and Galilean telescope. What's the difference in these two? The eyepiece. The Galilean telescope has a diverging eyepiece, whereas the traditional one has a converging eyepiece. And so let's talk about how these work. And believe it or not, I don't have any more slides on the telescope design. This is all going to be handwork here. So the first of all, we have the objective lens. You have an object. What's the location of the object? Let's say you're looking at a star. What's the location of the object? Yeah, object very far as we're concerned, distance object is approximately equal to infinity. Makes a real image. If the object is infinitely far away, where's the image going to be formed? At the focal point. So it's at focal length of objective. So if we look at this picture here, we have some object, and notice we show parallel rays. Why are they parallel? If you're really far away from something, the only rays that make it to you are virtually parallel. And so we have parallel incoming rays. But those parallel rays can come from different angles because we have something that's out there that's really big. So even though it's approximately infinitely far away, it's big enough that we can see light rays from here and rays from here coming from different angles at us. But they're all parallel, coming from the same location. And so here it's showing parallel rays coming from one location on the object. And because they're parallel, they're all going to form a focus at the focal point of the objective. So here is the image produced by the objective. Now in this picture, it's not set for unaccommodated viewing. If it was unaccommodated viewing, our eyeball is completely relaxed, where would the image be formed from the eyepiece? Where? Infinitely far away. And to do that, we would have the image at the eyepiece. So for a traditional telescope with a relaxed eye, you're going to have a real image at the focal length of the objective, and then the eyepiece, let me change colors. Has its object, remember its object is the image from doesn't spell that way, from objective at the focal length of the eyepiece. So image at minus infinity. So in that case, it's actually really easy to determine the length of a telescope, because you go objective out to the focal length of the objective, you have its image. But then that image is the object for the eyepiece, and it's at the focal point of the eyepiece. So you go focal length of the eyepiece. So the length of a traditional telescope, eyepiece, focal length of the, or not eyepiece. By convention, we almost always show light coming from the left objective is the one that's facing the object. So there's the focal length of the object where my intermediate image is formed. And then I'm going to have my eyepiece. I-E-C-E. Nice job. Nice job. Focal length of the eyepiece from that intermediate image. What's the total length of this telescope? It's just the sum of those two focal lengths. So the length of a telescope is just the sum of the two focal lengths of its lenses. Now we also want to calculate the magnification, not just the length. Calculating the length of the telescope isn't all that useful. Calculating its magnification, that's useful. So for the magnification, we come here and we have the objective, which is going to make an image for us, and the angle for that image is the angle that it would make with our eyeball if we were looking at it with the naked eye. So we don't have to take the distance from my eyeball to this thing that's approximately infinitely far away to try to find an angle. We can take that vertex ray and say this angle right here is the angle that we would have if we didn't have the telescope. And so using our small angle approximations, what is theta equal to? What is this side of the triangle? It's what? It's the focal length of the objective. So that's the adjacent side. That's the one on bottom. What is this side here? It's the height of the image, whatever that is. So that's the angle it would make if I didn't have the telescope. But the angle it makes with the telescope is, this picture is very confusing. Here's the angle it makes with the telescope. And what's, change colors. What's this distance going to be? If we have unaccommodated viewing, so the image is at infinity, what's the object distance going to be? Focal length of the eyepiece. And so theta prime is going to be the height of the image that was produced by the objective, since that's the height of the object here, divided by focal length of the eyepiece. And so magnification is equal to the angle with the telescope divided by the angle without it. Heights of the image cancel out, and I'm left with there's only one thing that I did wrong in this whole derivation. Anyone want to guess what that one thing is? It's the sine, because one angle was measured going clockwise and one angle was measured going counterclockwise. And so because I measured them opposite directions, I actually have to throw the minus sign in there to make them so they're measured the same direction. So that's our equation for the magnification of a telescope. So two equations. The length is equal to the focal length of the eyepiece plus the focal length of the objective. And the magnification is negative the focal length of the objective divided by focal length of the eyepiece. Now, when we talked about the microscope, I told you that the magnification only depends on focal length of the objective, focal length of the eyepiece, and the separation between them. The magnification technically doesn't depend on which one's in front and which one's in back. I told you if you turn around, it doesn't work right. Because you're going to have to make the object much farther away if you have a long focal length objective, and thus you're going to have the length of your microscope has to be different. It has to be a shorter length, which is going to then decrease the magnification. So for a microscope, you have to have the shortest focal length close to your object so you can get as close to it for the biggest magnification. For a telescope, very clearly, which lens needs to have the long focal length? What's going to make M bigger? A big number on top or a big number on bottom? On top. So that one's going to be the objective. So for a telescope, you want your objective to have a very long focal length, your eyepiece to have a short focal length. For a microscope, you want your objective to have a very short focal length. Your eyepiece still has a short focal length, but the objective is the really short one in a microscope. So the order of lengths for the focal lengths is reversed for a telescope versus a microscope. Hence, a microscope in reverse works kind of like a really bad telescope. But you have to make it really short compared to the length of your normal microscope as well. So that's the traditional telescope. Well, what's all special about Galileo's? Why would he do this? Any ideas? Well, here's the real nuisance with a traditional telescope. If I have an object that's a tree that's, on the other side of the Grand Canyon, and I look at it through my telescope, with the traditional telescope, the tree is going to be inverted because I made a real inverted image with the first lens, and then the eyepiece just magnified it, keeping it the same side. So I have an inverted image. Now, with the tree, you pretty much can handle that. It just seems kind of odd to have the tree growing downward. The Galilean telescope, having an eyepiece that's diverging, what can you tell me about the focal length of a diverging lens? Diverging lens? Okay, the image is on the same side, which means that its focal length is negative. That's what I was looking for. So this has a negative focal length. Actually, all of the geometry work we did is still correct for this Galilean telescope, but since the magnification has a minus sign here, and you have a minus sign in the focal length of the eyepiece, the overall magnification has a positive sign. That means it's not inverted. So this Galilean telescope gives you a non-inverted telescope. It's also a shorter telescope, so it has some advantages. So that's a design from Galileo. Now, just to make sure we're clear, a lot of people believe Galileo invented the telescope, and that's not true. Nobody knows the name of the person who invented the telescope. But we do know that it was created by people from the Netherlands, and Galileo heard about them selling these things that they had designed to be like party toys. You go to the party and you look at this and you're like, oh, look at that, it's so crazy. And Galileo heard about that and he's like, this would totally be awesome for science. And so he went and he actually went to try to buy one and they were already gone, so he couldn't buy one. But he got descriptions of it, and then he built his own and he improved on the design, and he was the first person to use them for systematic observation of the sky. So he didn't invent it. He did modify design, improve the design, and used it for science. So he is important with telescopes. It's just people think he invented it, and that's not correct. Look at this telescope. What's odd about this telescope? Yeah, it has 3 lenses instead of 2. That third lens, the one in the middle, is called the field lens. And here it says erecting lens, but the field lens is the traditional name for it. And that field lens has a purpose that's indicated by its name, erecting lens. The field lens is in there to take a real inverted image and create another real inverted image. So if you invert an inverted image, it's upright again. The erecting is upright erecting. And so that's going to give you an upright image as well. What's a negative about having a field lens? Yeah, it's going to be longer. And so that's a negative thing. You start getting a long telescope. You want it to be compact. There are some advantages, though, because let's say that you want to have a scope with a graticule that you can see where things are in that graticule. You have two focal points, two image planes, where it says first image and the second image. If you put a piece of glass there that has etched lines on it for your, you know what I mean when I say graticule? That's the little thing that has like a grid on it and says 0, 1, 2, 3, 4, 5 for measuring. So if you look through your microscope, you have something to measure with. You just put that at the focal plane, and then when you focus on your object, you'll also be in focus on that plane and be able to see it as well. And so this gives you an additional focal plane that you can play with for whatever reasons. This almost ends our optics talk. We're going to switch topics from lenses and ray optics to waves versus particles. There is a lot more on this area. You can talk about, lens systems and a pupil, an entrance pupil, an exit pupil, and there's a lot of things that go into optics besides what we've talked about. Just to give you an idea of what I mean by this entrance and exit pupil, have you ever used something like a telescope and the actual image you see is just this little circle? It's almost all black and there's just that little circle. You kind of move your eye around, it disappears on you. That's because the exit pupil is smaller than the pupil of your eyeball. And so the image is only filling part of your eyeball, and so you move around and moves around with your eye. Whereas if the exit pupil is bigger, then your eye can see the whole thing. And so things like that play into the design of systems. So it gets a lot more complicated, but this is as far as we go in general physics, because you know what we are? General physics, not optics class. So you could take an advanced optics class and learn all this cool stuff. It's really fun. Other types of telescopes, reflecting telescopes. If you are doing astronomy work, you are almost certainly using a reflecting telescope. Virtually every research telescope is a reflector. There are ones that aren't. The Green River telescope, is Green River? No, I don't know. The Yerkes telescope I know is a refracting telescope using lenses. But most telescopes are reflecting. They use a mirror for the objective rather than a lens for the objective. Now you still have all the same ideas and rules that we've talked about, but you're using a mirror instead of a lens. Can you think of an advantage to using a mirror? Okay, how about a disadvantage? Aren't you glad the weather's nice outside?
Yes.
Thank you. Just worried. Here are some advantages of mirrors over lenses. Advantage number 1, you only have to grind one surface with precision instead of 2. Advantage number 2, you can make them much lighter. You can make a big mirror that's much lighter than a big lens because you only need one surface. It doesn't have to have a thickness. Advantage number 3, mirrors reflect all colors the same. Lenses don't refract all colors the same. We saw dispersion. You've seen prisms that separate out the light. If you haven't, just go up to second floor, walk by Richard Clark's office in the afternoon. There's a prism that disperses the light out into the hallway so you see the rainbow. That rainbow is because the light of different colors is bent by different amounts because you have a different speed of light for different colors. But a mirror will reflect all colors the same. Yet another advantage, glass will absorb light. And if you have a thicker glass, it's going to absorb more light. But if you have a mirror, you can make the mirror have just a single front surface coating so you don't have to go through any glass that is very, very reflective. And finally, and most obscure, you can make a mirror that you can adjust. So for instance, let's talk about the James Webb Space Telescope. When the Webb Space Telescope goes up, which will be in probably another 3 years or so, it's going to have a really big mirror. And the mirror is built in sections. And I assume, although I don't know for sure, that they are going to use the technology to actually allow the mirror to adjust its shape on the fly. Now, I say I assume, but I don't know. If you're outside the Earth's atmosphere, you don't really need this, so maybe they won't. But on the Earth, you probably notice the stars twinkle. I talked about this, right? The stars twinkle because of the different temperatures of air causing light to bend in different paths. And they can take a mirror and they can deform it, either by having little pieces that they change the position or actually having actuators on a flexible surface to deform it. And they can adjust the focus so it stays focused even when the atmosphere is making the light change its path. So that's something you can only do with the mirror as well. So there are a lot of advantages to mirrors. Oh, one last one. I said they're light. You can also mount them much more easily because you can put a mount that covers the entire backside of a mirror because that's not part of your optical path. Whereas a lens, you can only hold the edges or have something obstructing to hold it in the middle. So there's huge advantages with mirrors. Another advantage is with the mirrors, now this here is a reflecting telescope and you see the path, the light comes in. Here's where you start the length for the optical path when it hits the objective. And then it comes out here and it reflects off of, this is actually the Newtonian design here. And it reflects off of an intermediate mirror. Then you go through an eyepiece and you have your image. Because of the light being reflected, your optical path is this distance plus this distance. The total length can be shorter. Or we could take a Cassegrain design. The Cassegrain design you have your telescope and you have your primary mirror back here, your objective, and then you have a secondary mirror here, and then you have, oh crud, I forgot with this I can't erase easily. I mean, I can erase the whole thing, I guess. I'll do that. So this here is my objective. This is a secondary mirror. And then the light goes, and then we have finally an eyepiece. Now, if you look at this, the optical path is twice the length of the telescope because the optical path starts, what location does the optical path start here? Where's the light start getting focused? At the objective mirror that's on the right-hand side. Then it comes out to that secondary mirror, reflects back. It's still being focused. That's still part of the length for the light path, but the light path doubles inside of that telescope. So the telescope is only half as long as you'd have to make if you made a refractor. So this is actually the design that is utilized in the vast majority of research telescopes because it uses space efficiently. Now there is an inefficiency. What's the inefficiency you see here? Yeah, this part here is blocked out. Now with the telescope, there are two things that you're concerned about. The two things you're concerned about are light gathering power and resolution. How many people are surprised there's not another word there? No one? What do you usually think about with a telescope? You usually think about the magnification, but I only said two things. The magnification is adjustable by changing eyepiece. So the magnification is not really a big issue because you can adjust it by changing the eyepiece. Furthermore, when you're using a telescope for astronomy, usually you're looking at things that are large enough that you don't need a super massive magnification. The problem is they're far enough away that they're really faint and that the details are hard to pick out. So the light gathering power is how much light it collects. In astronomy, we'll call a telescope that has a big objective a light bucket because it's just collecting a lot of light. But that allows you to see much fainter things. So the light gathering power is proportional to the area of our objective. Now in this case, the area, it's a circle, so it's pi r squared, and then you have to subtract the area that you blocked. So if you have a telescope that's, let's say, the telescope I have over here is, well, I have one that's 14 inches, and I think the other one's 12. So 14 inches in diameter. So its light gathering power would be 14 inches times pi, or 14 inches squared times pi. And then it has a little mirror in the center that's about, okay, well, that was 14 inches in diameter, actually not in radius. 7 inches in radius, so pi times 7 squared, so 49 pi. Then I have the centerpiece that's about 4 inches, which means it's 2 inches in radius, so that would be 4 pi when you calculate the area. Well, 49 pi minus 4 pi, that was a little bit less than 10% that I cut down on my light gathering power. And so that's the hit that you're taking, is having that light gathering power dropped a little bit. The resolution, we should see on Monday, depends on the wavelength of the light. Shorter gives you better resolution. And the diameter of objective. And larger is better. So when you look at these, what's going to give you the best light gathering power? A small or a large objective? Large objective. What's going to give you the best resolution? A small or a large objective? A large objective again. So a large objective gives you both of those things you're looking for, the light gathering power and resolution. The magnification is just the ratio of the lenses. You change the eyepiece, you change the resolution. So if you are in the market for a telescope and you want to use it for something like astronomy, you just want to buy the telescope with the biggest diameter you can afford, assuming that it has quality lenses. Right? If it doesn't have quality lenses, well, then you threw your money away. Right? So that is an important concern, but the biggest diameter you can afford is going to be your best telescope. Don't look at the magnification number. You just buy a different eyepiece and you change the magnification. Okay. So most telescopes that you buy for actual research are the Cassegrain design that I showed here, reflecting telescopes. A lot of the amateur ones, if you get a small telescope like a 6-inch telescope, they're usually going to be refractors rather than reflectors. But the larger ones are always going to be reflectors because they're more compact and you have all those advantages I mentioned. We use telescopes to not just look at visible light. Visible light is very clearly the thing you and I see when we look at the stars. But if you're an astronomer, you get different information from the different wavelengths. If you want to study something that's really hot, its peak radiation comes in the ultraviolet range or the X-ray range, not in the visible range. And so we have telescopes that are made to focus X-rays. And if you look at the X-ray telescope up there, you see that thing's bizarre. It's nothing like the telescope design I just talked about. The X-ray telescope has the barreled pathway, these things here that it's using to focus the light or the X-rays. It's very different. If you're looking at radio waves, then you have something like this. Some of us have these in our backyards. It used to be a lot of people had the big ugly dish, we called them buds for short, to receive microwave radio signals from satellites. Now we have these little satellite dishes that do the same thing. They're just not as big in diameter. What does that tell you? They're not as good because they don't collect as much. They have a smaller light gathering power, or in this case, microwave gathering power. So the bigger dish can collect weaker signals. That's basically the reason for a big one versus a small one. So for your satellite dish systems, they're not as effective at collecting, but these days they have pretty good LNBs, the receivers. And so you just have a single dish that brings it all to a focus. We're not making an image here. We just want to bring all of the radio signal together to one point so it's condensed, so we have more energy per unit area. So you're not looking at, oh, here's my image and it's this tall. You want to bring it down to a point. And so it's just a single dish, spherical in shape. What would the ideal shape be? A parabola would be the ideal shape. And let me tell you, those dishes are not simple spheres that you get anymore. The dishes, like the dish that I have at my house, it has 3 little LNBs, 3 different receivers. And it has a variable focus dish, so it is simultaneously focusing on 3 different satellites and focusing them different places, and that's why I have the 3 different LNBs to pick up the 3 different satellites it's picking up. And so they've put a lot of technology into designing those dishes to best focus the microwave rays. Now, I talked about resolution. If we're using a telescope for observing, then we do want to see an image, and we want to have resolution. And the resolution depended on 2 things. It depended on the radius or diameter here and the wavelength. Short wavelengths have better resolution. Resolution means the smallest thing that you can tell is there. So for instance, my vision is such that if I look at Jocelyn, my goodness, I don't know where that came from. Caitlin. If I look at Caitlin, I can see black spots where her eyes are, but I can't see any detail. I can't see that there's an iris. Right? I just see little black dots. Right? So my resolution is not good enough to see that detail. And so we measure resolution in the smallest angle that I can see the variation. And so the smaller the angle, the better my resolution. That's what resolution is measured. So it's measured in units of angle. And if you have a shorter wavelength, you can resolve smaller details. So in visible light, we can resolve things pretty good because what's the wavelength of visible light? In the ballpark from 400 to 750 nanometers, which is really small. If we were to go to infrared radiation, what's happening to the wavelength of infrared radiation? It's longer, which means the resolution is poorer. So if you have like a camcorder, the camcorder might have good resolution in visible light, and it might be able to pick up IR. It might give you night vision. They used to sell camcorders they called 0 lux because they could pick up IR radiation. Unfortunately, the perverts out there said, hey, your body is what's giving off the IR radiation, and so they put caps on that block the visible light, and then they take pictures of people's bodies with them. And so they had to change that real quick because that's not appropriate use of anything. So, but if you go to IR, you might be going up to 10 or 100 times longer wavelengths, which means your resolution is 10 to 100 times worse. The details that you can see are getting bigger and bigger and bigger instead of small. Well, if you get to radio waves might be 20 centimeters in length. Well, with hydrogen, I think is 1 point some centimeters in length. That's a pretty large wavelength. It means your resolution is really poor. So you can't see good details if you're using a radio telescope. But what can you do to improve the resolution of a radio telescope? You can't change the wavelength, right? You're looking for the information that comes from something that's cool. Hydrogen, you're looking at spin flip. You're looking at electrons that had their magnetic moment aligned against and then changing to aligned with the magnetic moment of the nucleus. It's a small energy difference. So you can't change that. So what can you change to improve the resolution? You can make a really big objective. And so that's why we have, like in Puerto Rico, the Arecibo telescope has a diameter, I think it's like 300 meters for its diameter. It's really, really big. Why? Because the bigger the diameter, the better your resolution. It allows you to get better detail. Now, this picture here goes with the next slide, a telescope farm. Now, this isn't an actual picture. This is an artist's impression of what the telescope farm looks like. But they have telescopes that are spread out. What would the point of that be? It seems bizarre to me. Okay, thank you for nodding and saying, yes, that seems bizarre. Well, what they do is they use what we call interferometry, which will be the topic, apparently, of our lecture starting on Monday, where they take the signal from one telescope and the signal from another telescope looking exactly the same place, and they superimpose them together. Superimpose, you can say either way. They superimpose them together, and then by combining the information, they can actually get a resolution that's equivalent to if they had a telescope that was the size of the separation. And so they have these things like this. You have a lot of them so you can collect more radio waves. And the resolution you're going to get is approximately the same as if the telescope was covering that entire piece of ground. So getting better resolution so you can see more detail. Yeah.
For that example, there were, the three different circles, their densities are different. Is there a reason for that? Or
I noticed that, and I don't have the answer, unfortunately.
Because the way I think about it is, if you're adding information, why don't you just have the biggest circle? Why don't you just have three of them instead of a smaller one?
And that's reasonable thinking. In fact, one thing that is done to get better resolution is you take a ground-based telescope, say an Arecibo telescope in Puerto Rico, and then you take a telescope that's orbiting the Earth, and you use interferometry between those. It's a much bigger distance than you're ever going to get with two ground-based telescopes, and you get that much better resolution. So I don't have a good answer for that, because you're exactly right with your thinking. I'm sure there must be some reason, but I don't know what it is. And it is good to have somebody ask a question I don't know the answer to. It's more useful than, well, yeah, sure. Okay, errors that occur with focusing. This is our last thing on the optics portion before we go to look at the wave properties and particle properties. We call the things that are problems with focusing aberrations. So the first one we have here is what we call chromatic aberration. Chroma means color. So it's bad focus because of colors. Well, what's the point? The point is, as we talked about, glass has a different speed of light for different colors. Because it has the focus, it all occurs because of the change in speed of light. If you have a different speed for different colors, you're going to have a different focal length for the different colors. And so that causes what we call the chromatic aberration. Now, we can correct it, but it's hard. You have to make two lenses out of two different types of glass. Different types of glass will have a different change in the speed of light going from red to blue. And so you make one lens out of one type and another lens out of another type. You do some pretty careful calculations. And you can make it so two different colors will focus the same place if you have two lenses. So now this picture would mislead you. This picture would have you believe that all of the light comes to a focus at the same place. No, it would just be two colors at the same place. So we call that a dichromat if you have two lenses making two colors come close to the same place. You can make a trichromat, where you have three different lenses made of three different types of glass with carefully calculated shapes. You have three colors all have the same focal length. That's generally considered pretty good. So another name for the
dichromats and trichromats is achromats. Achromat would be the ideal case of there is no difference in the focal length depending on color. So chromatic aberration, it's a problem that you have different speeds of light for different colors, and it can be corrected with multiple lens systems. But notice the word here, partially, not completely. Question?
What kind of problem would we have in a test with this?
You wouldn't. The only things you would have about what is a chromatic aberration, how do you correct a chromatic aberration? There's no calculation. So just the knowledge base. Off-axis astigmatism. If light is not coming parallel to the principal axis, you might recall when we started, I said principal axis, I'm going to do paraxial rays, the rays that are parallel to the axis or close to that. If they're not close to parallel, they focus off. And I showed you examples of that. So that's called coma or off-axis astigmatism. Spherical aberration, the spherical shape is not the correct shape, but it's what we usually use. And so that leads to the rays that are on the outside come to a focus here. The rays that hit near the center come to a focus out here. So you have different focal lengths depending if you hit the outer portion or the inner portion of the lens. That's it.